Okay, good morning, everyone, or afternoon or night, wherever you are around the world. Welcome to our workshop sponsored by the LA Tall Building Seismic Design Council. And my name is Silvia Mazzoni. I'm a part-time project scientist at UCLA and an earthquake and engineering consultant the other 32 hours in the day. I'm going to talk about today selection of and modification of ground motions for engineering design. I have a relatively long presentation. If you have questions, please put them in the chat so that we can address them. And maybe at the end, if we have time, we can have some discussion. And I will try to make time for that. So let's get started. So in today's seminar, my goal is to provide an overview and most importantly, an understanding of ground motion selection and modification for engineering design. But my ultimate goal is to focus on one thing because ground motion selection modification is an exciting and wide field. My focus is going to be on demystifying the Mean-Spectrum Modification Method. Often we call it mean-spectral matching. I go back and forth between the two. And I'll achieve that by describing the method, showing you what it can do, what its purpose is. It has a very defined purpose. And for fun, I'm going to talk about the many different things that you can do with it. And most importantly, also look at some effects on structural response. Now, why are we interested in this? Because in the very first two sentences of the LA Tall Building Seismic Design Council manual, it says very specifically that the intent of this document is to provide this and this and that for a structure subjected to earthquake ground motions. Please mute yourselves. And the point of it is to provide a more accurate identification of relevant demands in tall buildings. I really, really like this sentence because we tend to focus so much on just the ground motion side and variability on ground motions. And that's really what I'm going to be focusing a lot today. But how is that really related to the ultimate goal of structural response? And that's really what we still need to work on. And what you do on the ground motion side is simplified, simple mathematics, and then there's a whole big cloud that we need to figure out when we actually look at structural response and how are the two related. And that's really the focus of what I do outside of these hours, is trying to figure that out. And so code compliance is important. I'm working on a few issue teams for the BSSC building code, ASC 7. The LA Tall Building Code refers to ASC 7 with some additional criteria, but the goal here is really code compliance in terms of minimum performance objectives. And minimum that we're required to do is that the code requires a minimum of 11 record pairs for each MCE sub R compatible target. And I will describe what that is, okay? But there's a minimum of 11 ground motions. And most people, because of the types of programs that we're using, not everybody's using OpenSeas, 11 ground motions is already a lot of analysis and a lot of computation time. So we're limited, and most engineers are still using the minimum. So we like to be to do the best that we can do with those 11 ground motions. So the intent of these 11 ground motions in the old days used to actually use 3 and take the maximum. Before that, it was the El Centro record, right? So now we're increasing the number of records. Why are we increasing the number of records? We're increasing them because we want to have this range of ground motions that will give us a full range of ground motion characteristics for different fault hazards. And I will show you that, the different types of earthquakes that you're representing, as well as, different characteristics may impact different types of response in your structure. And so that's the purpose of the 11 ground motions. So what we can do on the ground motion side is we want these 11 records to represent the full range of characteristics, not just an average, but also a range of what's reasonable and what's not reasonable. So we look at the seismicity, the site response, but we also look at structural response metrics such as spectral acceleration, duration, pulse characteristics, anything that we think may be related to structural response, because that's the ultimate goal. And then in the analysis process and design process, that's what you do, is you evaluate this range of responses. So in the ground motion realm, we're looking at hazard consistent ground motions, but we need to pick these ground motions to represent the structural demand. So we kind of really want a response consistent ground motion suite, and how do we reconcile that? And we're still trying to figure all that out. And that's what's exciting about the field of ground motions, is that it's not just a seismicity problem, it's also structural or geotechnical response. I'm a structural engineer, so I will focus on geotechnical, but I'm structural, but geotech has the same issues. So we've got this 11 ground motions. All the young kids in the world these days, you're all taking statistics, and 11 ground motions is not a good statistically significant number to capture both the mean and the range of response. And we're not just looking, even though the building code focuses on the mean, it also checks for maximum response and maximum drifts. So you really want to look at both the mean and the range. And so I have an example here on the top left. I've got 50 records that I've selected for a target spectrum. So you'll see these figures again and again, all a little bit different from each other. And I plotted log just because it shows the full spectrum of ground motions. But we're looking at a response spectrum where we have spectral acceleration on the left and on the vertical axes, a period on the horizontal axes in seconds. The spectral accelerations is the response of an elastic single degree of freedom damped oscillator with 5% damping. Okay, that's what a response spectrum is. Design spectrum is, and I will show you how that's calculated, is representing of the hazard of what kind of ground motions are expected at your site. And that's represented here in the red in this figure. And so what we do in the ground motion world, we select and scale and maybe modify the ground motions so that the average of our suite of ground motions, the solid black line, is at or above our design spectrum, which is the red. That's our target spectrum. It's not always your design spectrum, in a certain period range. So here I've shown an example, between 0.1 and 10 seconds, but that's defined by your structural period. And that's the band where we're trying to make sure that our ground motions are at or above this design spectrum, because the design spectrum or the target spectrum kind of represents an envelope. And then I'm plotting in the dashed black line, mean plus or minus 1 standard deviation. So that gives you an idea of the variability of these ground motions. This here that I'm plotting is what I call the spectrum resultant. So this is a ROT-D 100. And so typically you're working with 2 horizontal components, and the ROT-D 100 is the maximum projection in a 360-degree space. Okay, this is what we use in design these days. So we are looking in 2D response, but we represent it by 1 maximum direction spectrum. Okay, and that's what you will see again and again in these figures. So if I've got 50 ground motions, I expect that to be the best representation. But what's interesting is if I go to less records, what if I only go to 20? My match on the mean is actually better than if I had 50 records. All right. And the way there's 2 ways of selecting records is what you can do is you select the records, you compute what we call the mean square error, which is the error between your ground motion spectrum and your target spectrum. Okay. So best fit is really the general term. So if I pick the 20 records that have the best fit, you see the figure here on the top. All right. And you can see that the mean is a pretty good fit in the period range that I'm interested in. And it's almost better than if I had 50 records. Okay, because with 50 records, we're widening our magnitude range, our distance range, and there's so many different parameters that control the response spectrum. There's so much variability in response spectra that it's almost the more records you have, the more variability you have, but then the farther away you are from your target spectrum. And if I so these top in the middle are the 20 best fit, but look, if I even pick something below 20 other records that I just randomly select within a bin that meets my criteria, now I have more variability, which can be good, but I'm not matching the target spectrum at all. If I go down to 11 records, which means I only pick the 11 best records that have the best fit to my target, actually my mean right here is my best fit to the mean. So the fewer records, which kind of makes sense, right? The fewer records I have, if they meet you know, the criteria, pretty much if your target spectrum is consistent with your selection. If you're making a good selection, the fewer records, the better you can control the match to the mean, but you have less variability. Is variability good or is it bad? That's what we've got to figure out. And what should that value really be? And if I pick 11 other records, just kind of randomly from a bin, or you can actually write a program that optimizes and finds the best fit for both the mean and a target sigma, you can do better, but you will never fit the mean as well as you do in this case. Okay. And so 11 records is something that is actually reasonable when we're doing something that we're trying to match the mean, but they're not giving us that variability that now is everybody wants. Why do we want variability? Is because when we look at a response, you look at acceptable responses, and I will show you a slide on that. And so it's become really the topic as what do we do with this? Something we're looking at for the building code, something we're looking at in research, and everything in between. And this is the realm, the 11 records is the realm where the mean spectral matching method is king or queen or empress. All right. If we had more records, you might be able to match the mean better, and then you wouldn't need to do this mean spectral matching. But again, I've kind of shown you that the more records you have, the harder it is to match it. So I think it's helpful in all the realms. And all it is just an additional step, and I will show you that. So if we look at the 11 records, these are the 11 best fit records, and we look at the mean. So we compare the black line and the blue line. Gosh, those are really close. That's really, I mean, that's a really, really good fit. Okay. If I look at my 55 records to zoom in, it's a really good fit in some parts, but it's not a really good fit in the extreme periods. And that's something that you will notice mainly because of how you're trying to fit lines to match a certain line. It's always in the middle that you get the best fit, and it's the extremes that you can't fit it so well. Okay, and so you'll see this even in 50 records. So many records is not really going to solve the problem. So if we go back to our 11 records, what we want to do, what the building code says, is you need to scale the suite such that the average, so the black line, is at or above your target spectrum. So we actually kind of need to bump these records up. Okay, and what we find out is we look at what point, you know, it's pretty much you figure out at what point does an overlap, and it's in this long period range that it bumps up all your records. And so you actually have to bump it up by 32%. Okay, so even though your best fit starts, you know, with certain scale factors, to be able to meet the code in that period range, and I picked a wide period range, is never really that wide, you actually have to design for 32% higher forces. Now the building code, and that's a problem. And it's a problem only because of that one tiny little point in my long period range when I had such a good fit everywhere else. But one important thing, you know, the building code says when you've got scaled records, you can actually go below by 90%. Okay, there's a little bit of latitude. Well, if I take 90% of 1.32, it's still a 20% increase. Okay, so even though when you have scale records, you're given a little bit of leeway there, you still have to bump up your records by 18%, just because of that one tiny little period. So that's where the mean spectrum matching comes in, is it's going to touch these records. And I don't know if you can really tell the difference between the two figures, between the blue curves on the left and the ones on the right, but I've tweaked them just a little bit, so that now your red line or your black line in my modified records is right on my target spectrum. And that's all the mean spectral matching method does in its fundamental objectives. It modifies, or it gives you targets to modify your records just a little bit, just so that your design spectrum and your average of your suite are right on top of each other. Because average, according to the building code, is done in linear space, this is pretty straightforward and easy to do. And it's actually easy to automate, and I will show you how to do it. Okay, but that's all it does. All right, it's modifying the mean and modifying these records just a little bit, tweaking them here and there so that you're right on the target spectrum. This could be done if you're using a CMS. This could be done if you're using a uniform risk spectrum, whatever spectrum you have as your target spectrum. And you have to start with a good selection of ground motions. The better the selection is, the less modification you have to make. Okay. And that's pretty much all the main goal is of the mean spectrum modification method, or mean spectrum matching, because we're matching the mean. Okay. Now, its objective, as I've said, is it allows you, when you have only 11 records, or 50, what the heck, okay, just to capture both the mean and a range of response. You can even control your standard deviation, and I will show you that. Now, remember, this is only in the realm of spectra. Okay, we're changing the ground motions in the spectra. We need to figure out, how does this modification affect your actual structural response? And I'm going to look at that to see, does it really change things significantly, or can we actually predict that? Okay, and so it's just allowing you, it's just simple math, straightforward math, to adjust the record such that the mean and the sigma equal to your target. I'm not prescribing what that sigma needs to be. Oftentimes I'll say it preserves or maintains the variability, because if you don't do anything, you maintain the variability of your scaled record. And so it really depends, where your variability depends on what you started with or what the target is that you define. I'm not saying anything about what the variability should be. The mean spectrum modification method gives that to you in your hands to be able to control it. You can bump it up, you can bump it down, and I will show you that. And again, as I said, why is variability important? We're all talking about it now, because when we look at, this is another chapter 3 in the LA tall building seismic design cancel code. It talks about acceptance criteria, and it also compares it to ASC 716. And ASC 716 pretty much checks the averages and the mean response and this and that, but also looks for unacceptable response. What's really your maximum demands on your element? And that's where the variability comes in. And so my structural engineering friends are like, no, don't give me so much variability. I like, tightly matched or very small variability, because that doesn't give me so much variability in my response. But is that important? Is it not? That's a decision to be made outside. I'm just giving you the ability to control it. And that's the whole goal of this. And the LA tall building, the Seismic Design Council allows unacceptable responses, and it just does other checks. And so each building code, though, is looking at these maximum responses, and they manage it differently. But that's why variability in the ground motion is important, because variability in the response is important. And so the very first thing you can do, the very fundamental part of the mean spectral matching, is what I've already described to you. You've seen those two top figures, is just slightly changing the ground motion records so that the average is your target. Now, if we look at variability, so I'm plotting in the bottom axis the sigma, which is the standard deviation of those records divided by the mean. And I'm plotting them for both the component, H1 and H2. It's actually direction X and Y, only because sometimes they're fault normal, fault parallel components. And so that's the sigma for the two directions, as well as in red, the sigma for the, resultant for the ROT D100. As you can see, they're on top of each other. Whether it's their scaled record or their modified record, if all I do is play with the mean, I'm not changing the variability that I had in my ground motions that were scaled. And that's why I say, it preserves it or maintains it, because it's the same variability. But if you want, you can control that. And so now you can say, hey, I want a little bit more variability in my records. You can do that with some additional math in your linear combination, when you compute the average and the sigmas. And so now you see the figure on the right, and only in that period range, and I know it starts to look weird when you only do certain period ranges, I've stretched out my spectra. And so now if I look at the mean, I'm still right on. And if I look at the sigma, of the spectrum resultant, which is the solid black line, I've got the 30% that I defined. Okay. And so I have to say right now for ground motion modification, we use RSP match. This is something that you would do at your end. And it's not always trivial to modify records to match the ROT-D 100, but using, you know, the two components and the ROT-D 50 gives you something pretty close. So you may not get exactly that 30%, but you'll get pretty darn close to that. Okay, this is more projected. But that's what's neat is you can, oh, you don't like if your, whoever's your peer reviewer says your ground motions don't have enough variability, you've picked too few. You can either go back and select a different suite that now you have to readjust the means and, you know, you may have to give something up, or you can implement the mean spectrum modification and say, hey, bump this up a little bit. So I've got the same records, I'm just modifying them just a little bit. And that's the point of it, but you define that 30%. And you get to define that 30%. That's what's really cool. And so if you zoom in to that plot that I showed you, we're not losing, we're not changing the variability in the components, as you can see, which is important, or it has significance, but you're really changing the variability on the resultant. And that's something to think about and process and see what those effects are. Norm Abramson, so there is what used to be called the tight spectral matching, and I'll show you a figure there, where you modify every component of all your records to the same target spectrum. Norm is now, if you ask him for ground motions, he's going to say, no, there should be no variability in my spectrum resultant, because that's how the PSHA analysis is done, and this and this and that. And he's got some valid points on that. So you can actually modify, and you can still use a mean spectrum modification method so that now your sigma is equal to 0. And so now you've got no variability in your spectrum resultants. It's right there in that period range, but you still do have variability in your components. And the ground motion prediction equations are all based on the spectrum resultant. They're not based on the components. So there's the argument that you should still have some variability in your components. My problem is with this is that you're still modifying the records too much and taking away their natural shape. And I will show you that in a future graph. But even just the mean spectrum matching or modification is just a little extra mathematical step that's pretty straightforward that allows you to play with your suite of ground motions just enough so that you can meet the code without having to go to these extreme scale factors. Okay, and this is just zooming into that. Now, if you want, you can go to the other extreme and bump it up to 60%. I want a lot of variability. I feel like this is what the FEMA 365 ground motions look like. Okay, too much variability, but if you want, you could do that. That's just a number that you input into your little math calculator. And now you can bump up your variability. You have the same records and you still have maintaining, and you know, the modification is not so significant. Of course, I'm plotting it log, so it doesn't look like that way, but you can do this. And of course, you know, there's certain boundaries as to how far, and you always have to look at your modified records to make sure that you've done it right. Okay, that's a whole other art in ground motion modification. If you want, you don't have to make your sigma constant. You can even make it period dependent. So you can come to something close like the mean, you know, the conditional mean spectrum or any sort of other variability that you want. You know, you're playing at each period, so you can actually do something like this if you want. Okay, and so that's the overview of, that's all the mean spectrum modification method does. I want to kind of go back and look at a little bit more of the basics of ground motion selection, just to, because as you will get into conversations, people will ask certain questions, and like I skipped the part, well, what if you've got, why is the spectral shape important on the individual records, for example? Well, that's because you may be needing to represent different types of earthquakes. You may be in a site where you've got subduction and near fault. And so you need to have different spectral shape. And so in ground motion selection, pretty much the whole process for nonlinear analyses is 5 steps. You compute your target spectrum, select your ground motions, you scale or modify them, Then you apply them to the model and post-process your analyses, run the analyses and evaluate and this is typically done in a loop, which is also why you don't want to have to run too many ground motions, because you never just run your ground motions once, even if it's just 11 of them. Then the geotechs come in and they give you ranges for the soil springs. And so you double the number of analyses and everything in between. So ground motions for nonlinear analysis in the process, the very first step is you compute your target spectrum. Your target spectrum is dependent on your site. It can either be site specific, which is a geotech will give you, and they've got much more detailed analyses of your site, of the seismicity, better approximations of the VS30 and all those properties. Or you can go to the USGS design maps that are getting better and better, especially now that they're looking at multi-point spectra. They're bringing in more points on the VS30. And so they're not site specific. They're not as good as what the geotech will give you, but they're a really good place to start. And it's, it's included in your taxes. So that's a great place to start with. And then your target spectrum is not always going to be your design spectrum. All right. Your design spectrum can be if you're looking at risk targeted MCE, if you're looking at the uniform hazard spectra for some other conditions, but it can also be the conditional mean spectrum, where now your target are 3 different spectra. You can still use the Mean-Spectrum Modification Method after you've selected your ground motions, even for the CMS. And so I want to make sure that you guys see that there's a difference between your design spectrum and the target spectrum for the ground motion. Sometimes they're the same thing, but they're by definition 2 very different things. Okay. Then once you looked at your site, and before I showed you LA, but this is actually on the right, is the deaggregation for a site in the Pacific Northwest, because I needed some diversity. The geotechnical, if you get a site-specific analysis, the geotech will give you the deaggregation, or if you're going to do ground motion selection, you need to ask for it. If you're doing it from the USGS, they actually have a web tool. They have a web services tool that's awesome. Okay, where it's going to tell you what is the contribution to your hazard at different periods, different VS30s for your site. Because, the faraway subduction earthquakes will affect your long period spectra, but not necessarily your short period spectra because of attenuation and things like that. Okay, so when you select ground motions, you need to make sure that your ground motions are representing the hazard. So you're going to need some ground motions that represent the faults. Gridded is typically like a fault is when we don't know enough. They just kind of smear some sources that are lower magnitude. And so that oftentimes controls in areas where you don't have faults. You can have fault sources. So those are your NGA West 2 type crustal events. And then you've got some slab and some interface. So those are the subduction earthquakes. And so when you've got your ground motion selection, you need to make sure that you've got a certain number of events of records from each one of these events. And so now you may actually need to have more than 11 records if you have so much diversity in there, but just for you to have an idea. In different types of sources and site have different spectral shapes. So if you do this tight spectral matching where you squeeze everything to have the same spectral shape, you may lose some of the characteristics of different types of seismicity. And so it's important when you're working with ground motions, when you're communicating with your geotech, to understand what each event is represented by the different ground motions. So you'll have some subduction and maybe not. You can then download the ground motions from the wonderful, excellent online tools, either for the crustal events from the NGA West 2 and NGA East. I put that out in 2014. And then in the last year, I've also put out the NGA subduction tool. It's not on the same webpage, it's elsewhere, but if you just Google it, it's easy to find. That's where you can get your subduction records. And even there, it has a tool that allows you to select and scale ground motions. It's important to take all the characteristics of your site, regional seismicity, and all these different characteristics in selecting your ground motions. So I wanted to just put these basic concepts. As a structural engineer, you kind of want to have an idea of what's going on at this end as well. Now, we go back to my initial points where I was just giving you an overview. Now you as a structural engineer need to select, maybe the geotech will make recommendations, what kind of modification you want to do. Do you want to do amplitude scaling? In the old days, in the building code is very specific on what to do if you have amplitude scaled or tightly spectrally matched records. And there's a penalty for one and an adjustment for another. But with the mean spectrum modification method, and what I'm calling the spectrum resultant matching, which is the spectrum resultant matches the target for all of them, there really isn't anything specific on how to manage these in the building code. And so that's what I'm working on with the BSSC is how can we have an issue team on how can we bring this into chapter 19 or 21 of ASC 7. Okay, and so you get to decide what you want to do. Amplitude scaling or modify the frequency content of the record in these 3 different standards. It's important to keep in mind, as I've already shown you, that these 3 different methods control the mean, but you can also control the standard deviation on them. And so that's a choice you make as a structural engineer. And I can't tell you what to do, but my recommendation is to go with the mean spectral modification because you're meeting the target on the mean as well as the sigma, instead of, completely destroying your sigma. But maybe you want a sigma of equal to 0. That's up to that's a big topic that needs to be resolved still. So amplitude scaling this is my selling point for amplitude scaling. Amplitude scaling is still the best. If you have tough peer reviewers, this may just be the best way to go because they can't argue with it. So a lot of structural engineers will go with that. It's interesting because you're not modifying the records other than an amplitude scale, but now you're changing the amplitude without changing the duration and other characteristics. So it's not like it's perfect. And someday when we've had all the earthquakes, or maybe when we start bringing in some physics-based simulation records, we can fill the gap on scaling. We don't have to apply these large or very small scale factors. But that's still the advantage of amplitude scaling. What's great about it is, other than amplitude, you're keeping the characteristic period and energy content of your record. So you can see here, I'm guessing right here, these are either my subduction records or my pulse records. And typically when you have a peak in the long period, they're relatively low in the short period. And when you have a peak in the high period, maybe you have less amplitude in the short period. And so it's great because when you're amplitude scaling, you're maintaining that subspectral shape. You're maintaining the variability between the different records and also the variability between period to period. Those peaks and valleys are important when you have a yielding system or you have a non-yielding system, even better. Okay, and so when you're amplitude scaling, you're keeping that. The problem with amplitude scaling is when you're losing a limited number of records, one record can influence everything. And that's why oftentimes structural engineers will go to the geotech and say, oh, I don't like this record, give me a different one. Okay. Meeting the code can lead to unreasonable scale factors, which is what I just showed you earlier, just to meet it in that one little point. It's very sensitive to your initial selection of records. All right, it can give you very different results and different averages. And so you kind of need to iterate on that. And it may lead to high energy content and higher modes. Look at these spectra. I've got 4.5 Gs in my short period range. Is that high? I don't know, but that's pretty high. And that just comes with scaling the records to meet one period range, and you've got other period ranges that may be affected. And this would be okay if you had a single degree of freedom system, but when we're dealing with multiple degree of freedom systems, you may be overexciting higher modes. And so that needs to be taken into consideration. But amplitude scaling is wonderful, and this is what most engineers do because it's the easiest way through, and we haven't demonstrated a benefit to other ground motion modification procedures. As you can see here, as I said, it's very sensitive. I've just picked 2 different suites and scaled them differently, and I can go all the way up to 8 Gs almost. Okay, so it's very dangerous, especially when you do the scaling at one period, especially with the CMS, that can get very dangerous with your scale factors or just your high amplification at the longer periods. The other end of the extreme is the traditional component tight spectral matching, as you can see here, but even the one with 0 sigma, let's say. Okay, every spectrum resultant is right on your design spectrum. This is nice because it's objective. Anybody's going to give you exactly the same results. Okay, there isn't any sort of controlling and decisions to be made. It minimizes the amplification of higher modes. I'm going to argue that it actually brings up higher modes in some of the records too, though, right? And you're not bumping it up, but you're also not bringing it down. It reduces the variability. It removes, it's an advantage. It removes these peaks and valleys in the spectrum, and it meets the building code. So this was how it was done in the old days when that was the only option other than amplitude scaling. This got rid of a lot of problems with amplitude scaling. And we were only concerned about the mean. And so this was the best option at the time. Okay. And again, structural engineers, we don't want variability in the records. So maybe this is the right answer. The limitations are, it's a significant modification to the record. You're putting in some additional frequencies that didn't belong there. Maybe it was a subduction earthquake with a long period frequency, and now you're having to add in all the short period waves and excitation, which you're going to see in your multiple degree of freedom structure. You lose a lot of these characteristics for each record. The energy is uniformly distributed. These are almost just different ways of seeing the same problem. And you've got no variability between the records and between the periods. Maybe that's a good thing, but it's a little scary when you're coming in by looking at these spectra. Also, they don't always give you the scale factor. So maybe this was something that was scaled 10 times or something like that. So make sure when you're getting something modified, make sure you get the scale factors that are computed. They should still be there. Typically, even just a scale factor on the PGA is a good place to start. Okay. And these records are therefore considered unrealistic. I don't know if it's the structural engineers that consider unrealistic or the geotechs and seismologists, but this isn't really what we see in nature. And so there was a lot of pushback against tight spectral matching. And so if we put those things together, the advantages of one, the advantages of the other, and we say, okay, what do we like about this and what do we like about that? We end up having a description of the mean spectrum modification, right? So the improved method will ensure that the average of the spectrum resultant closely matches the target spectrum at all periods of interest, right? So we get that from the spectrally matched or from the tight spectral matching. We don't want to modify the record. So we get that from amplitude scaling. So we'd like to be close to the amplitude scaling. We want to, keep the characteristics of the ground motions, which really means we want to modify them the least amount. We don't want to amplify the higher modes too much. And that happens when we have to impose these really high scale factors. We want to maintain the record to record variability. Again, you're not maintaining the natural that we don't know what it should be, but you're keeping the same variability that you have, and you see it in the figure on the right. That comes, this is what you have in the amplitude scaling, and we have it. We want to preserve that. And then there's additional things that you can do is you can maintain the variability. You can also achieve targets for 2 different directions. You can actually play with that. And you can achieve a target that you like for the standard deviation. So this is all our wish list, which then becomes the answer, which is the objective, and that's what the mean spectral matching does. We match it at the mean, but we meet all these other requirements that we want to reduce the peaks. And you see, it's a really nice shape of spectra. You can't even tell that these are modified records. If you look at the displacement trace, you'll notice it. But you don't see it so much in the acceleration, and definitely not so much in the spectra plotted in log space. Okay, and so it's just a construct, which goes back to the construct. My real question is, are we doing the right thing in selecting ground motions to meet, your target spectrum? That's a whole other answer. But the mean spectrum modification allows you to do this with a limited number of records, or even with a large number of records, to really meet your desired goals for the ground motion suite. And so if we compare them, I mean, which one would you pick? This is a comparison of the averages on the left and a comparison of averages and ground motions. You can definitely see the advantages of this scaling here on the mean. When you have amplitude scaling, it's really difficult to meet that with the record. And then the shape of the spectra, even keeping the peaks low with the mean spectral matching is really, and then again, it's not a selection method, it's just an additional step that you do to your ground motions. And so let's figure out how to do that, okay? It's just math, okay? And there's 10 steps that you can put it into your Excel or into your Python or any sort of program you want. I've actually programmed it and developed a tool, of course. And so you calculate your target spectrum. You got your spectrum resultant of each ground motion pair. So this is the same if you're doing scaling. You scale the ground motion records individually so that they're closer to your target spectrum. So this is the same step as if you're doing scaling. You calculate the average of your spectrum resultants, right? Because that's what you would do in scaling. And so at this point, you're fine. It's the same. You haven't done anything new. But now, and I'll have a figure in the next slide, what you're going to do is you're going to calculate at each period, you're going to calculate how much you need to adjust the mean to be right on to your target spectrum. And you compute these factors at each period. And then you take these factors, because an average is a linear combination, so you're literally just adding these up linearly. The same factors in linear space, you can apply them to your individual records, and therefore you can apply them to your individual components. And that's kind of the assumption that you make, but it works. And then you can do some additional work if you want to do some directionality, compute additional factors if you want to play with the variability at this point. And then you take these factors, you apply them to your spectra, and you run them through RSP match. Instead of having one target spectrum, in the old days with RSP match, you put one target spectrum and take these 22 ground motions and match them all to the same target spectrum. Now you have to do a little bit more bookkeeping because each record is going to have its own target spectrum. But that's all it is. It's just bookkeeping. Very easy to program it. And then you've got your records, you recompute the spectra, and you may need to do like a tiny little adjustment to make sure you meet the code, because as I said, it's not perfect. But that's all there is to it. So graphically, this is where you start. I've amplitude scaled my records to meet the mean square error, though, okay? You don't need to be above the target spectrum. Once you're at this point, this is the one slide. All the other slides today are just fillers. This is really the key slide that tells you exactly what you need to do. So at each period, you compute how much you need to bring down or up or down your mean to be right onto your target spectrum. You pull these little numbers out, it's a little array, and then you apply them to your components. So in some parts of your components are going to have to go up, sometimes they go down, and then these new values become the target for your spectrum, for your ground motion modification that you do in RSP match. So it's pretty straight from the implementation of it, it's pretty straightforward. The difficulty is, what are your choices for target spectra or target, variability, or do you just keep what I call the natural variability of your ground motion suite? But that's something that's great because you can control it. If you modify the records, I'm cheating, I'm showing you the acceleration, but you can barely really see the difference, especially if your initial suite, especially when you've got your target spectrum and you've picked just the right ground motions that meet your criteria. This is not always going to be easy because your target spectrum and your design spectrum may be controlled by subduction in some periods and be made controlled by different sources in other periods. So it's never super clean as if it was just a simple magnitude 7 at 15 kilometers where we have enough data. But it's a lot better than doing an extreme tight spectral matching. And then if you look at the records themselves, those same amplification factors are applied here. And so you meet the code, you may need to bump up, a couple percent points just to make sure that you're at or above your target spectrum. The current problem is ASC 710, if you go by the book, says that spectral matching has a 10% penalty, and therefore some reviewers will make you do a 10% penalty on this, but I know most engineers have managed to work through it with their peer reviewers that this method does not deserve a 10% penalty because you still have the variability. And I think a lot of people have managed to get that done, to not apply that. And that's kind of my goal here, is to make sure that peer reviewers and everybody understands the method and how it's harmless, quote unquote, so that it's understandable and people can actually accept it on projects. Because that can somebody be a stalling factor why people may just go to amplitude scaling. Or some geotechs don't apply. What's really, really cool, I think it's exciting, is if you're looking at soil structure interaction and you've got your kinematic effects reductions in the short period range, now you need to do some serious modification to your records in the short period range. This is easy to do, just applying this concept of, modifying the mean. And so it's great for kinematic effects and soil structure interaction ground motions, because it's difficult to get ground motions that are measured that already have the baseline averaging and embedment effects in them. So this is a great tool for this. Also, as I pointed out, here's plotted in linear scales. It's a little bit easier to see. You can actually control the variability in your records. And I've gone through this point already and shown you the different applications. Also, if you really want to, you can have different spectra, different targets for the two different directions. Okay, in the old days, this was important. Now, going to ROT D100, this is not so important anymore. But maybe if you're doing specific projects, you can actually just get your, the point of it is you can get your hands in and just set different target spectra from your records. And that was just the concept, oh yeah, you can do that, was really the game changer. Everything else is just math. And so in summary, the method is really just looking at the average level. You're minimizing modification. It's important to have a good initial selection. It's code compliant. And then there's just, you can use it with whatever, and I've already given you the selling point on it. Now, I want to kind of go quickly on, because I'm really an open seas person, I'm not a ground motion person. I built my own little open seas model from the SAC 9 or 10 story building. And I ran elastic and an inelastic ASC 41 type of structure. For the elastic, I ran ground motions at 5%, inelastic 2%. This is show you that the structure does collapse if it wants to. And so I did the 4 suites that I've shown you. Okay, amplitude scaled, match only the mean, therefore keep a variability, 30% and 0% variability. These are what the ground motions look like, just to give you a summary, to be didactic here, but I've shown you these already. Components, there's variability in all the components, so that's a cool thing. And I'm plotting, and I'm just trying to see if I could see a pattern, if I was trying to see if I could see something. And so what I've done is I've plotted the elastic and inelastic just displacements at each floor. And then I'm at each peak, that's why I was looking for that function yesterday. I grabbed the peaks of those displacements for the top floor, and then I'm plotting the shape, the deformed shape at each one of those peaks. And I'm trying to see, wow, am I exciting the higher modes? Am I not exciting the higher modes? And this is kind of just a very quick and dirty way of doing it. And so on the 4 columns, you have the 4 different methods. And so I think this is the direction that we need to go to in evaluating ground motion selection and modification. It's not just looking at the spectra, but looking at the response. And so I just kind of want to show you some cool graphics, just because to show you that the first, if you look at the second row, you can see that it yields in all 4 methods, but differently. I have different types of residual displacements. And so I have very different responses. And you can see it even in comparing the very bottom row. I have very different responses in the different ground motions. What I can see in this figure right here, where I have sigma equals 0, hey, look, I've got a higher mode excited here, okay? So are these ground motions exciting the higher modes? I don't know if this is the way to look at it. Maybe we need to do a little bit more detail, but I just was trying to plot things. And my point of it is we need to start looking at structural response, not just the simple math of these simple single infinite systems. So this is kind of exciting. Look at these kind of cool shapes that you are having. And so I was seeing these higher modes in all the different methods, not consistently. So this is just really just a quick review on them. And so I just did this for a few different ground motions to just kind of show that the responses are different. I've changed more than just the spectra. I've changed the structural response significantly. Okay, and we have to be careful because the math is easy, but the structural response is what's really important. And then I also just did some plots about, interstory drifts of how they're distributed. And I think the summary one is this one right here. I think it's interesting. On the left-hand side, so what I've done is I've computed the maximum interstory drift, at maximum absolute interstory drift of every story for every ground motion. And then I computed the envelope, which is what you see on the right-hand side. So those are the maximum interstory drifts that you will see. And then on the left-hand side, I actually computed the mean of each set of ground motions and the plus or minus one standard deviation. Am I getting different responses? I'm not going to look at this one case and say, oh, look, that black line, which is the mean spectral matching at 30% has the highest demands. The point of it here is the demands are different and they're going to be very much specific to your building. And what's interesting is that the distribution of the means is actually pretty close. Is that close enough? I don't know. And the variability there, we see it differently. But according to our single degree of freedom elastic model, the one with the sigma equals 0 should give us no variability in response, but it actually does. And it almost gives us the highest variability sometimes. Okay, so we need to figure out how to connect structural response of real buildings, especially tall buildings. Well, tall buildings then become a whole different thing, but with what we're doing with these ground motions. And I think that should really be the focus of what we want to look at in the future as well. Personally, I would like to, instead of matching on the mean, I would like to match on the envelope. This is more consistent with hazard. In this case, the more variability you put in your records, the lower your mean can be, right? Because you're enveloping. And so maybe it could be a give and take. You have little variability, you have the highest average. You put a lot of variability in your records, your average goes down. And so this is something that I've been thinking about and I'm trying to push. And so that changes the whole concept of what we do with ground motion modification anyways. But this is my personal little project, one of my many. And so in summary, mean spectral modification allows you to develop a suite that's a little bit more code compliant, makes your life just a little bit easier. It's not the answer to everything, it's just a little extra step that I recommend to not modify your record significantly, okay? Because even amplitude scaling, you're changing the amplitude, and that's a lot to ask of a record without changing the other characteristics. And so it minimizes modification and maximizes control. Right now, I'm working through the code compliance and peer review concepts, so I'm trying to get it out there and understood. I think that's kind of the goal why we're doing this presentation. And the math is easy, and you can do it yourselves, but of course I developed an online tool to do this. Now there's a couple of caveats, but it's not really about the method itself. And I've said this many times, we're basing all our ground motion selection on these elastic dam single degree of freedom models. I think it's time we move beyond that a little bit. And so we need to reconcile this PSA world of response spectra with nonlinear response of multiple degree of freedom systems. What are the ground motion parameters that matter for structural response? And then also the question right now of the day is, how do we quantify what this variability should be? And so this doesn't answer this, it just gives you the tools to deal with that. I developed a tool online. It's a pay-per tool per use. I'm trying to get this business started. So if you go to my website, you could find it off. You've got a promo code. I think it's a pay-per-use type of license. It's not that you have to buy the yearly license, because I think it's great because you can charge it to a project. And so this is online, and I've got it up there. And I think it's great, but I could use some feedback from users if anyone's interested. So that's my hour. I hope I've gotten some messages across about ground motion selection modification, that you understand what the mean spectrum modification method does. And kind of open to questions at this point here in the room. Maybe we could start if not someone calls in the question too.
Yes, now come so that I'm close to the mic so that other people that are not here can hear me. Thank you very much for your presentation, number one. Just a clarification, I have a question, a clarification. It is correct that there is a penalty in ASC 716, chapter 16, ASC 7.
That's the chapter.
And PATBI for mean spectrum modification, but there is no penalty in LA tall building, a structural design guideline for using this method.
Thank you.
Yeah.
Yes. Thank you for doing that.
So the opening questions, audience, if you have questions, come to the mic or
Come to the mic.
yeah, or your question should be repeated. People online should put it in the chat.
Okay, so let's somebody, I can always repeat the question. Anybody have questions or comments?
This is Mike Marine. May I ask a question?
Yes.
That was a beautiful presentation. Thank you so much. I learned a lot. I think I understand the beginning and the end. I'm just not totally understanding the intermediate step. When you apply the different factors, there are no unique solution to that. There are many ways you can bring down that average at the particular period. Are you using the same factor for all records, or using a weighted average, or applying it to the ones that deviate the most, or are there any acceptable methods to do that?
Okay, that's a really good question. So if your goal is just on the mean, and therefore your very first step, it's the average of the spectra for the building code is done as a unweighted average of all the ground motions, right? You take the sum and then you divide it by n. So they all have the same weight factor. And therefore, yes, if you're only playing with the mean, you apply this scale factor that you have here from the figure. This is on the average, and therefore applied on the average needs to be applied to each record the same amount. Now, if you want to change directivity, directionality, some of them, so for example, for pulse records, they say you can't modify the pulse records. Well, then maybe we'll leave the pulse records alone and only modify the other records. Then maybe you may need to do a little bit of numbering, but here there is a unique solution if you're only doing with the mean. If you then want to play with the sigma, then yes, you have individual scale factor or modification factors that become record dependent. Yes.
And my second question, I'm sorry.
It's a unique solution for this case.
Once you've decided for each record what the factor would be, the method in which you make that change in the actual record, is that constant? Everybody uses the same thing?
Well, so then that becomes the art of it, and you've got to make sure that you are doing this properly. You would do, because we're working in a damped response spectrum domain, you cannot do a Fourier transform and apply the modification in the Fourier world. You have to do it in the time domain. And everybody uses RSP match, I believe, which was developed by Norm Abramson. It's a tool that's kind of, he doesn't have it in his GitHub, but I think everybody's got a copy of it. Most geotechs have a copy of it. Or I think there may be a version of it in GitHub that you can actually compile yourself. And so I think it's a standard. It's that tool. And yes, different people do it differently. You've got to make sure, because there's steps on how to do it. I learned how to do it from Easy Frisk, because they had an algorithm on how to do it. But it is an art. But the great thing about it is that once you've applied it, you compute your response spectra. And if you match the spectrum, that's the first checkbox, yes. And then you need to look at your displacement, velocity, and acceleration time series to make sure that they're reasonable. But there isn't really a yardstick or a measure that we really know. ourselves on what should be realistic or not. But as long as you get the right spectrum in the end, which is not a trivial step, it's a kind of thing, don't try this at home, but it's actually pretty cool to do yourself.
Can I add just one?
Yeah.
One RSP match, as Sylvia mentioned, is the standard. There is for lazier persons like me. There is another software out there which is pretty user-friendly for matching. It's called Seismic. If you search it on Google, you'll find it. It's not free, but it's cheap, but it's very user-friendly.
It's done by your Italian friends too.
Yeah.
Do they do it in the time domain though, or the frequency?
It's frequency domain.
Oh, you see, that's
matching. It's a matching thing. Yeah.
Well, but that's the thing. So frequency domain is different. And so when you're dealing with signals, you can work in the frequency domain.
Yeah.
When you're working with ground motions and your target is actually a response spectrum that's damped, it's not a one-to-one relationship. And so what RSP match does, it does it in the time domain by adding wavelets. And so he's adding or taking away wavelets.
Actually, the Seismic match has various methods and you can pick the one you want to use.
Yeah, and honestly, because RSP match is open source, I wouldn't be surprised if they've implemented it themselves and you're paying for the UI. So yeah, I'll look into that. That's good to know. But yeah, it needs to be thought out.
So in the period range that you are trying to match, how many periods do you take to manage this? And will it change depending on how many points you get?
Yeah, so what I do is, I mean, you've got the NGA record at the 111 periods or 140, depends on your period range. And so I would do it at those periods. And your target spectrum, you can just interpolate it at those periods. So it's more periods you try to do it, the slightly more work for the program to do it, but it's automated anyway. So I would pick the most number of periods. And then you could just interpolate in between for your target spectrum.
We have one comment on the chat that says that Seismic match actually does it in the time.
Oh, good, good. Yeah, it's published work and it's open source. So yeah. Does that answer that question about the periods?
Yeah.
Okay. Yeah, I would do more only because then you don't have so many tweaks and things. But that's what you do when you've got some periods that don't look so good. You only show a few periods and then it looks cleaner. But I think you're okay. I'm kind of, I was reading the building code and they're saying to do linear interpolation between periods instead of log interpolation. So that kind of threw me for a loop. So I need to go and change that in the building code too. But yeah, I would do a log interpolation on the periods anyways, and for the target spectrum.
Any other questions for Sylvia?
Thank you, Sylvia. This is Ashi. I learned my structural dynamics from Ray Clough back in the 60s. So I'm still locked onto structural performance issues and dynamics of this whole selection of time histories. What do you think about selecting the time histories based upon the structural response for a site-specific condition, which include the site period? Because amplitudes are pretty well quantified by USGS, but site period has been a fundamental issue because it can change. As I observed during the Northwoods earthquake back in '94, the site period can change within a few hundred feet by a very large factor. So my emphasis has been in focusing on the site period. And what do you think about structural response matching with the selection of time histories?
I'd have to look into it a little bit further. I haven't spent enough time looking at the concept of the site period and selecting ground motions. So I'm not gonna, the trick is, in the end, we're bound by our code compliance. And so if you have a method that allows you to meet the code, then we need to evaluate it from a structural response. I mean, you're still talking about site period. Isn't site period going into your seismic hazard analysis anyways?
What I do is I don't like to force my opinions on nature. So I try to look into the scenarios, what can happen from a different fault or kinds of fault rupture, especially we see in Southern California, and
Yeah.
try to assure that the response is consistent with the applied motions from that aspect, and then worry about code compliance. Because my fundamental focus is on structural performance.
So first of all, I love your background. Two is, this is not real. I mean, we kind of have to, the struggle that I have is when then people nickel and dime what we're doing to try to match nature. But this is a model. This is a numerical model. This is a mathematical model. And we need the mathematical model to be consistent with what you're doing in the analysis, what you're doing in the ground motions, what you're doing in the hazard. And so, yes, nature, we either use nature 100% or picking it in some cases and not others, then maybe our models are not consistent. And I think that's what we need to focus is that our models need to be consistent with each other. And so, for example, this whole concept of response spectra is a made up model, but at least it's consistent and it gives us all the language to speak in and we can compare the different things. So that's my take, but I'll let you speak.
And thank you again for your great presentation. I have learned a lot, but I like your PDF file of this PowerPoint to absorb it a little more, to get it, you know, to clearly understand more of it. If it's possible, if you can send me a PowerPoint PDF of this presentation, that would help.
Okay, we're going to work on making something public.
Thank you so much. Yeah.
Thank you. Oh, there's also a World Conference paper from 2012. That one has the fundamentals, actually. That's where I would, it's a short 6-page paper that says everything. And people are trying to get me to write a spectra paper, but I think that paper says it all. So that's where I would really, it's a lot more details about how I do it in the World Conference 2012, something like that. Yeah, so if you look at
I'll try to find out.
Mm-hmm. Any other questions?
Sylvia, this is Zia.
Hi, Zia, how are you?
Fine. So what I found out that many building requirements of 11 records is not very straightforward. There are requirements of pulse record, there are requirements of fling effects, there's requirements of multiple sources impacting the same. So once you get initially when you started with some records and when you end up, then what I found out in some cases that even mean spectral matching is not helping much compared to scaling because of all these other requirements.
Yeah. So it's interesting because these are the topics that we're talking about in our issue team. But so it's sometimes when you've scaled your records and you've got a good suite, you almost don't even need this mean spectral matching. And then at the other extreme, I don't know, because I feel like when you've got these pulse records, right? But what is it going to be? So if your site at most 30–40% of your records are pulse, and so you can actually, the mean spectrum modification can help you with the other records. So you don't have to just apply it blindly to all of your records. And so to me, it's just another tool. It's not the answer to everything, but I think it can actually make your life better in certain things. But you're right, it's not the blanket answer for everything, especially, you know, with fling effects for the, and other considerations like that. But I think with the pulse, I think I've always recommended to just not modify those records. And then you compute your average, almost like do the same process, but then don't do it to your pulse records. And you'll see that you'll actually still be okay, especially because the pulse records are bumping things up over there, or maybe don't modify it in that period range. Or sometimes the modification is so small that you're, as long as you're not losing your pulse, maybe you're bringing it down just a little bit.
All right.
It allows you to do that. So you have to use this tool carefully. You know, you can use it as a blunt pencil, or you can sharpen it however many. It's just math. It's really all this is math.
Okay, thanks.
Mm-hmm.
Any other questions?
We have one here in the audience.
Yeah, should I walk over?
Walk up
Yeah,
to the
you
podium, please.
I just wanted to pick your brain on more physics-based simulation records, and as those become more prevalent, Do you think that this method will be useful for that because we'll be using still a limited selection of those, or do you think that will eliminate the need for modifications like this?
It's so this is it's blind to whether you have what your ground motion record is, whether it's physics-based or not. It's independent of it. Again, it's just an additional tool. Now, if we have enough simulation-based records and we still don't, where your average spectrum is right on your target spectrum, then you don't need it, whether they're physics-based or they're measured. If you have a scenario, if you're only just doing it for that magnitude 7 at 15 kilometers, you pick your records and it's there. But maybe you may need some play with the variability. Maybe maybe it's too much variability. You may get too much variability or incoherency from these records. And so again, it's just the idea of what you can do. That's all this method is saying. Hey, you're not bound to one thing or the other. Play with the math of these spectra and play, and make sure that you're not, make sure you keep an eye on what goes on down the road, that you're not really damaging your records, but you're not really doing much. The closer you are to your target, the less you have to do. So.
With that, I want to thank Sylvia again for a great presentation.
Thank you.
And I want to thank everybody who came here physically to attend this workshop and everybody online who joined us with this. And I hope to have more of these soon. Thank you all.
Thank you.